No, I mean that'll be up there as soon as I do it. It's been a busy time. So last time we proved one of the very nice theorems about polytopes. We proved that if you have a d-dimensional polytope, and it's a lattice polytope, meaning that all the vertices have integer coordinates, then this Erhart polynomial really is a polynomial. In other words, if you take your polytope and you scale it by a factor of n, and you count lattice points in there, then that function of n is a polynomial. Okay? And we discussed how that's equivalent to saying that if you look at the generating function for those numbers, then it's given by something like this. So some polynomial divided by 1 minus z to the d plus 1. Okay. So we already proved this, that if P is a lattice d-polytope, then the Erhart series looks like this. But what I want to do now is prove something stronger, which is called Stanley's non-negativity theorem. Which says that all of these numbers are non-negative. Actually, they're not only non-negative, but they're non-negative integers. Okay. So that's what I want to prove next. And maybe I'll tell you that this thing is, it has many names according to who you ask, but sometimes people call it the H star vector of P, or the delta vector, or the Erhart H vector. Okay. But that's what I'm going to prove. Okay. So, I mean, one reason that I want to prove this is that it's an interesting fact because it tells you what kinds of things can be Erhart polynomials. Okay, so if you take a polynomial and you make the generating function and it looks like this, then if it's going to be an Erhart polynomial, those coefficients have to be non-negative integers. Okay, so that's one interesting thing about it. I think it's a nice result in itself. And the other reason is that in this proof I'm going to introduce a proof technique that we're going to use for another important theorem next time. Okay. So, okay. So here's a proof. So if you remember, we actually did this for simplices last time. So for simplices, the way that we proved this formula without this condition of the non-negativity is that we first proved it for simplices, and then we said you just triangulate. Okay? And for simplices, we saw that these numbers were exactly the number of points in each level of the fundamental parallelepiped. Okay? So for simplices, we did it. We did this for simplices. Okay. And so then the next question would be, can we then just triangulate and say that we have it for everything? So can we then just triangulate? In other words, can we say that if we want to compute the Erhart series for a pentagon, can we just say, well, just take this guy triangulate it in whatever way you like, and then do what we did last time, right? So this plus this plus this, but then I double counted this, and I double counted this. Okay? So is this a proof of this theorem? That's the trouble, right? The trouble is that I'm introducing minus signs. Last time I didn't care about whether these h's were positive or negative. I just wanted them to be numbers. I just wanted there to be a polynomial here. And for that property, it's fine. But if I want to prove that these things are non-negative, then I'm in trouble because I know that these things have positive coefficients here, but then I'm subtracting other positive things. And so then the question becomes, you know, is this more positive than this? That's what it kind of comes down to, right? So the trouble is the minus signs. Okay. But then we're gonna do it anyway, but we're gonna do it in a clever way. So here's a trick. So we're going to take our triangulate. We already talked about how we can do this either for the polytope or for the cone. Okay, and it's going to be useful to do it for the cone. So I'm going to triangulate cone of P as the union of different cones. Okay? But now what I'm going to do is this. I'm going to shift my picture by a small, and let me for now say irrational vector epsilon. So this is going to be hard, but maybe I'll try to draw a picture even though it's hard. Let's say that the cone that you had was this one. Okay? And so then I'm saying triangulate it in some way. Okay, maybe by introducing this diagonal and splitting it into two simplicial things. Okay? Now, what I'm going to do then is just shift this picture a tiny bit in this direction. Okay? Just shift the cone like this. So I shift every one of these little points. And then I take this cone over these guys. Okay. And so what I have here, this orange thing, is the cone of P shifted over by a vector that I'm going to call epsilon. Okay? And so then, of course, this triangulation still holds true if I shift everything by epsilon. Okay? But now, what I want you to, the way that I want you to think about this is that we're trying to capture all the lattice points in that black cone. So think about it. If I just take that apex and I move it over by a tiny bit, then those lattice points are going to be exactly the same. Okay? So the idea is that I'm going to consider the lattice points in this shifted cone okay, and then I'm going to say that actually if the shift is tiny and it's kind of pointed in the right direction, so I really mean to shift it kind of in the direction opposite of the cone, then this orange cone is going to contain all the lattice points of the black cone and no others. Does that sound believable to you or not? It's very hard to draw. I don't know, maybe I should draw a lower dimensional picture just so you can at least see what's happening here. So if I have some cone like maybe this one, our favorite cone, then you see if I just shift it over by a tiny amount and I just move it over here and I keep the same parallel directions, then of course the orange cone contains the black cone, so it contains in particular every lattice point in the black cone, but you see if I move it a small enough amount, then it doesn't contain any other new points. Okay, so I think here it's more believable in 2 dimensions, and 3 dimensions is a little bit harder to see. But I mean that's precisely the point. That's precisely the point, that if you look at the lattice points on this hyperplane, you know there are some lattice points, and then if you look at the next hyperplane in that direction that has lattice points, it's a discrete distance away. In this case, the next one is this one. Because so my point is that there aren't any lattice points on the boundary, and the reason is that if you look at the next line with this slope that has lattice points, it's going to be this one. And if you look at the next line in this direction that has lattice points, it's going to be this one. So as long as I don't move that far, then I'm not going to contain any new lattice points because I have that direction in the orange. Okay. So that's what happens in this picture, but let's prove that you can actually do this. Okay. The point is the following. The point is that here, this cone is given by inequalities of the form, I don't know, ax less than or equal to 0. Remember that if you have a cone, then the cone goes to the origin, so all the inequalities, the right-hand side is equal to 0. Okay. So then, what are the inequalities of this thing? The inequalities of epsilon plus the cone of p are basically of the form a times x minus epsilon less than or equal to 0. Right? I just shift the variable over by epsilon. In other words, ax is less than or equal to a epsilon. Okay? So now I want to say something a little bit more precise. I want to say, suppose that epsilon is in minus the cone of p. So you see that's what I mean when I say I want to push kind of in the direction away from the cone. So I want to push in a direction that is contained in the negative of that cone. If epsilon is in minus the cone, that means that, I mean, the inequalities for minus the cone are the inequality is ax bigger than or equal to 0 for minus the cone. And epsilon satisfies them because it's there. And that means that all of these things are positive. Okay, a epsilon is bigger than 0. Okay? But epsilon is tiny, so these numbers are all tiny. Okay? So the inequalities of this cone are ax less than or equal to 0, and the inequalities in this cone are ax less than or equal to tiny positive numbers. Okay? Now, the thing is that this is a lattice polytope. This is a lattice cone, and that means that I can choose all the inequalities to be integer inequalities. Okay? So I can choose A to be an integer matrix. So if A is an integer matrix and x is an integer number, then ax is an integer. And for an integer, it's the same thing to be less than or equal to 0, but to be less than or equal to 0.001 for integers. Okay? So even though the cones are different from each other, when you restrict to the integers, they're the same cone. Okay? So that's the first trick, that if you kind of shift over by a tiny real number, you don't change the kind of integer structure of the cone. Okay? So that's my first trick. Shift it over a little bit. Not yet. And by the way, I haven't even said what irrational is. And I don't know what an irrational vector is because I don't know how to divide vectors. So, but for now, I have only used that it's small enough that all of these numbers are less than 1. And I have used that it's in minus the cone. But I want also to say that it's irrational. And in what sense do I mean that? In the sense that I choose epsilon, so it's not on any hyperplane spanned by rays of my cone. Okay? So what I'm saying here is that I want to shift my point over. I want to shift the apex of the cone, but I don't want it to lie, for example, on this. You know, the thing is that I'm about to cut the polytope through this slice, right? Through this kind of blue slice here. Okay? And I don't want my orange point to be on any of those planes spanned by vectors in the cone. Okay? And this is where I say, well, for example, if I choose this thing to be irrational, and I'll say what I mean exactly by that in a second, then again, because these kinds of planes are spanned by integer points, that means that their equations are rational equations. And that means that an irrational point cannot be on such a hyperplane. Okay? So the point is that here I have finitely many hyperplanes to avoid, and they're of the form a1x1 plus dot 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 plus a d plus 1 xd plus 1 equal to b, where all of these things are integers. Okay? And so then I want to make sure that epsilon is not on here, and so then, for example, I could choose epsilon to be 1 comma pi squared, or something like that. And that way, there's no way that it would satisfy a linear equation with integer coefficients. Okay, so for example, choose this thing to be, I just say it in words. Okay? If you choose x1 to be something involving pi, x2 involves pi squared, etc., xd plus 1 involves pi to the d plus 1, then if this equation has solution, then you would have found a polynomial equation that pi satisfies. And you might be aware that pi is a transcendental number that doesn't satisfy any integer equation. So I mean, this is overkill. Tristram, maybe you're not completely convinced that this is worthwhile. It's overkill, but it's one way of doing it. Okay. But another way of doing it is just to say there's finitely many conditions, and you can clearly stay away from those finitely many hyperplanes. Okay. So the point being that if you look at, okay, now let me say it like this. The point is the following, that if I now take maybe I'll just draw a picture of the identity that I want to now say is true. Okay? That if you look at sigma sub this cone, so remember that sigma is the enumeration of all the lattice points. Okay? Then I'm saying that my first step is that this is the same thing as sigma of the orange cone. Okay? The irrational cone. Okay? Then I'm going to triangulate that one. Okay? So I get sigma of something plus sigma of something, and then I overcount it. Okay, so the first one that I get looks like this, right? With this, plus the other one is this one. Okay, I mean I'm basically cutting along this diagonal. And then I overcount it, right? So I overcounted the points in the intersection. Okay. But you see, the beauty of this is that this is an irrational cone. I mean, this, before we translated it, it was a rational cone. But now we shifted it over by some irrational number, by some irrational vector, and that means that there's absolutely no lattice points in here. Okay? There's no lattice points. So this is equal to 0. And this would be true for I mean, this is a simple example, but it would be true in any dimension. The way that you would do this is that you would always add up the full dimensional contributions, and then you would subtract double counting. Okay? But in the way that I chose my point, to my shift vector to be irrational, I get that these lower dimensional contributions don't contain any lattice points, and so they just disappear. Okay? And so I just get a positive sum of these things with no minus signs. Okay? So this is sigma of my cone of P. Okay? And then when you translate this into Erhart series, what you're going to get is that the Erhart series of P is the Erhart series, is basically the sum of Erhart series of simplices. Okay. And then because these are simplices, they satisfy the theorem. Okay? So that means that each one of these things is a positive polynomial divided by 1 minus z over to the d plus 1. So when you add them up, it's still a positive polynomial divided by 1 minus d to the d plus 1. And that's the end of the proof. Slick, right? It's and it's almost like you did nothing, but then you really just kind of got rid of all the issues. I mean, all the issues of science, by just shifting by a tiny irrational vector. By the way, I might be wrong, but I think this proof is due to Matt Beck and Mike Devlin and maybe Frank Sotile. So he has a paper called Irrational Proofs of Three Identities, or something like this. And he basically gives slick proofs like this of results. So that means that this is a very new proof. This is maybe like 5 years old. I mean, the result is old. Is an older result due to Stanley. This is a nice, clean proof.
There's only one small thing to prove on that, right? Every facet of that dimension of the contained node.
Mm-hmm. Right.
Every hyperplane that you choose.
Right. And you know the way mathematicians are. So when you read this proof in the book, when he gets to that point, he says exercise 3.7, right? And I'm sure that's what the paper says too. It's easy to see that. I mean, it requires a proof, and I'm sure if you go ask him, he can prove it for you. So that's just kind of the way mathematical writing is. Anyway, so this is the theorem. This is the theorem. It's nice. And I wanted to say a couple more things about this, because I told you already that whenever a combinatorialist sees a natural number, immediately we think, okay, what am I counting here? If it's a natural number, it must be the answer to a counting problem. Okay? Are any of you topologically inclined? If a topologist or if an algebraist sees a positive integer, what do they see? An invariant, or so a topologist probably sees a topological invariant, like genus. An algebraist probably thinks of a dimension of a space. And so I just wanted to tell you that, because there's a very beautiful new theorem that there's no way that I could explain to you in an hour what this means. But at least I want to tell you that it exists, and that if you're interested, then it's going to take you some work, but I mean, there's some definitions, but basically, HI is, so what I should tell you is that if P is a lattice polytope, then there is a very beautiful construction that constructs something called a toric variety. Okay? And here we're living in algebraic geometry. So I mean, what's a variety? So the simplest example of a variety is if you have a system of polynomial equations, then the set of solutions is a variety. So for example, a parabola is a variety because it's the solutions to y equals x squared. When an algebraic geometer talks about a variety, they mean something more complicated than this, but you can kind of think of it as piecing varieties together. Take one variety, you glue it to another one according to some rules. And there's a very beautiful way of constructing a variety out of a polytope. And what's really nice about this is that you get this family of varieties. They're called toric varieties, and they just behave a lot more nicely than a random variety, because there's a lot of combinatorial structure behind. And there's a huge theory, and many people have careers on this. The career is to try to explain algebraic things, geometric things, topological things about the variety, and relating them to the combinatorics of the polytope. Okay? And Mustata and Payne, I mean, this is not their theory. This is an older theory, but they have a very nice result that says that HI are what is called the stringy Betti numbers of XP. And Betti numbers are kind of the, I mean, there's several meanings for this in topology, but they basically are the numerical measures of your space topologically. And so what this says is that if you want to quantify the topology of the variety with respect to these Betti numbers, then the numbers that you get are precisely the numbers that appear here. Okay? So this is a very nice result that tells you that even if this happens, even if you're a geometer or a topologist, sometimes you get stuck with combinatorics because things are connected and you don't get to choose what field you're on because fields don't care what fields they're on. So, but anyway, so I think this is a very beautiful result. It's very recent. I think this is also like 5 years old, and they actually then used this to disprove a pretty famous conjecture about Erhart polynomials through algebraic geometry. And you know, it's again another nice topic if you're inclined towards these sorts of things. Okay. But I should tell you that there's really a very nice dictionary between properties of the variety and properties of the polytope. So this is, and in particular, this idea of lattice point counting in polytopes arises very naturally from the varieties. Okay. So that's just a little bit of kind of, I don't know, sales. Okay. So let me write another lemma that I think is useful. The Erhart polynomial of P is given by H0 times T plus D choose D plus H1 times T plus D minus 1 choose D plus etc. plus HD T choose D. This is some formula. It basically tells you that if you have the H star vector, then you have the Erhart polynomial in a very explicit way. Okay. And the proof. Well, you can imagine what I'm about to do, because this Erhart series is exactly the generating function for this thing. So all I need to do is just take this thing and multiply it out and get this. That's what I'm about to do. I'm about to make a mess, but sometimes you just have to do that. So Erhart, I mean, actually this is not too messy. It's not too bad. If I do this, the generating function for the Erhart polynomial, by definition, this is the Erhart series. Right? And this is equal to, by this result, the summation of hi z to the I from I equals 0 to D times 1 over 1 minus z to the D plus 1. Okay? Now, if you flip back a few pages in your notes, you're going to see that we already computed this series. I mean, what we said is that this is just the binomial theorem, right? This is just 1 minus z to the minus d plus 1. And we did that, and what we got, so we got this nice formula. This is what we got. Okay. That's the Taylor series for that thing. And so the coefficient of, I mean, we're looking for LP of t, and that's the coefficient of z to the t. And it's basically going to be all the ways that you can form a z to the t from here and here, right? So what you do is you need I and j that add up to t, and then you put hi times j plus d, choose d. Okay. And then you'll see that what I wrote here is exactly that summation. I mean, basically, I'm choosing a subindex here and a number here that add up to I plus j plus d or t plus d. And so you see here, I get 0 plus t plus d. Here I get 1 plus d minus 1, d plus t. It's exactly the same summation. And that's the end of the proof. Okay? It's just a computation. But let me make an observation about this. And pay attention to this observation because you'll find it useful in the homework. If you look at these polynomials, t plus d choose d, t plus d minus 1 choose d, t plus 1 choose d, and t choose d. Well, I'm calling them polynomials. Can you see why they're polynomials? Maybe you've thought about this and you know that these are polynomials. If you haven't, well, just think that by definition this is, I mean, basically just write it, you know, x times x minus 1 times x minus 2 up to x minus d minus 1 over d factorial. The d factorial is a number, and the top is a product of d linear functions. Okay? So each one of these is a polynomial of degree t, of degree d. And it is a fact that these form a basis for the space of polynomials of degree d. So this is a basis for the polynomials of degree d. At least we have the right amount of polynomials, right? Because if you're degree d, that means that you have d plus 1 coefficients. The coefficient of t to the 0, of t to the 1, up to t to the d. So the space of polynomials of degree d is a vector space of dimension d plus 1. And here I have d plus 1 things. So at least it has the potential of being a basis. And I'm telling you that it is a basis. Okay? And I think you're going to want to prove this in your homework. And it's not hard, actually, by induction through the usual identities for binomial coefficients. But the thing is then that what I'm doing here, I mean, we kind of have this preferred basis for polynomials of degree d. We like the basis 1, x squared, x cubed. But maybe somebody else has a different favorite basis. Maybe this is their favorite basis. And if it is, then all I'm saying is that Erhart polynomials have positive coefficients under this basis. Okay? So I'm just saying that this thing has non-negative coefficients with respect to this basis. Okay. And again, let me make another kind of rough comment about this, which is that it's possible to prove that if you have this property, then, I mean, this is a polynomial of degree d plus 1. So it has d plus 1 roots. And it's possible to prove that if a polynomial has this property, then that is very restrictive on where the roots can be. Okay, this gives you restrictions on the roots of the Erhart polynomial. Okay. And one reason that I tell you this is that there's this very interesting conjecture. It's not even exactly a conjecture. It's kind of like an experiment. So here's an experiment. Remember this matching polytope from your homework? Let's call it B sub n. Polytope from your homework. The matching polytope. So if you consider the Erhart polynomial of that polytope, it's just some polynomial. Okay? And I don't know whose idea this was, but someone decided that they were going to plot the roots of this polynomial, which sounds like nonsense if you... I mean, not like nonsense. You can do it, but you have no reason to expect you're going to get anything nice. But it turns out, and it's crazy, it turns out that the roots kind of look like this. For all values of n. This is not an accident, it just happens. And this is an observation and no one understands it. Okay. But the roots, I mean, this is the complex plane, right? The roots are complex. And the roots look like this, okay? And this is a completely unexplained phenomenon. And, you know, one hope was that maybe you can do this kind of thing to prove things about the roots, but who knows? No one knows an explanation. So this shows that there's a lot here that we don't understand, basically.
You know why they did matching polytopes?
Actually, I meant to, no, I don't know. I don't know. And I don't know, I mean, I think this would be a nice kind of computational experiment to just compute thousands of Erhart polynomials and graph the roots and see what you see. Actually, I think that's what happened. I think Jesus de Loera just did this and he got these nice answers for these guys. But I don't know how nice the answers are for other polytopes. So. Okay. So another point that I want to make is that one very open problem is to basically explain what these vectors look like. Okay, so we know that they are positive or non-negative integers, but we don't really know what restrictions they satisfy. Okay, and there are many conjectures about this, and there also are many conjectures about the roots of the coefficients of the Erhart polynomial. Okay, so in the usual basis, we can write the Erhart polynomial as CD t to the d plus dot 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 plus C0 t to the 0. Right? And here's an easy fact, is that C0 is equal to 1. That we know the last coefficient is always equal to 1. But here's another nice result. The last coefficient is exactly the volume of the polytope. And this is one of the punchlines of the name of this book, Computing the Continuous Discretely, because this is very much we think of it as a continuous function. You know, the way that we define volumes. I mean, I haven't defined it, but you know the definition. And the definition is not really very illustrative. That's it, right? The integral over the polytope of the identity function. We think of it as a very continuous thing, but here we're obtaining it through this very discrete process of counting lattice points and polytopes. We're just saying, count lattice points and polytopes, you get a polynomial. The leading coefficient of that polynomial is the volume. The proof is not hard, actually, because what we do is this. Let's say that you have a polytope. Okay. Now, really, what does this mean? This is this whole business about Riemann zones, right? Really, the point is that the way that we compute volumes is that we just cut up into very small rectangles, or in this case, parallelotopes, and whose area we know, right? And in particular, what we can do then is just, you know, look at a grid. And then, for each lattice point in the grid, let's make a little square around it of size 1. Okay? So when you do that, then you see basically you get some approximation of the volume. Okay? So the idea is that the volume is approximately what you get by adding up all these little cubes. Okay? But now what do we mean by approximately? What we mean is that you want to take smaller and smaller and smaller cubes and then repeat this process and then take the limit as the number of cubes goes to infinity. So the way that we can do this is that we can say, take your grid and then make it into a finer and finer and finer grid. Okay? So let's say that this is not really the integer lattice. Let's say that it's the integer lattice, but scaled by 1 over t. And then let's send t to infinity. Okay? So the idea is that this is approximately a number of lattice points in P times the volume of each one of these little cubes. And what's the volume of each little cube? Well, we're in d dimensions, so it's the length to the d. So 1 over t to the d. So let me actually write an equation that is true. Volume of P is the limit when t goes to infinity of number of points in P which are in the lattice 1 over t z to the d divided by t to the d. Okay. Now, looking at lattice points in the 1 over t grid that are in P is the same thing as looking at the normal grid, where instead you scale the polytope up by P. So instead of scaling down the grid, let's scale up the polytope. It's going to be the same thing. Okay? So I could just scale the polytope by t and intersect with the normal grid. And I'm going to get the same number of points. It's a bijection that takes P to t times P. So I get this. And the beauty is that this is precisely the Erhart polynomial, right? So limit as t goes to infinity of cd t to the d plus cd minus 1 t to the d minus 1 dot c0 divided by t to the d And what could be easier than computing this limit, right? This is CD plus a bunch of things that go to 0. So we get that the volume of P is equal to the leading coefficient. So that's the proof of that. I should also tell you that, what do we know about these coefficients? We know that this one is equal to 1. The last one is equal to 1. We know the first one is the volume. We know the second one. And the second one is the surface area, if you can imagine what that is like in n-1 dimensions. It's the surface area divided by 2 for some reason. And there's some other scaling factors that are a little bit subtle and are about the kind of number theory that goes in behind here. So it's surface area divided by 2 multiplied by some number theory factor. Okay? And that's all we know. We don't really know anything about the other coefficients.
Other certain vagaries of 2, I think. The volume is the lattice point deep in the interior. You know you're going to count as 1. So the lattice point near the boundary, half of the time it's in, half of the time it's out.
Yeah, that's a good kind of heuristic argument for why 2, because if you're somehow imagining that on the boundary the cubes are kind of half there. So you get a contribution of, that's basically the idea, is that the main contribution is from all the interior cubes, and then the next degree contribution comes from the boundary, and it comes from all the cubes that are around the boundary, and each cube kind of contributes half of the cube. So that's why you get a half. And then the number theory, I think if you draw a picture, you can see why a little bit of number theory comes in. But basically everything about this is open too. So
in 2 dimensions, couldn't we use fixed theorem to find the surface area?
You see, in 2 dimensions there's only 3 coefficients. So that means that in 2 dimensions we understand this perfectly. 1, volume, and this number that we just said. Yeah.
Nothing about the surface area. I was thinking of it as generalizing fixed theorem.
Yeah. So we're going to talk about Pick's theorem in a class or 2. But if you don't know what it is, if you know what it is, let me just tell you that it only works in 2 dimensions. That's one of the news about this. You might hope that there's an extension. But the point basically is that it doesn't, and we just know 3 coefficients, and that's why Pick's theorem works. But that's why you go 1 dimension higher, and then we don't have something like that anymore.